Okay, so number 7. We have alpha is 0.09 for a right tail test. So again, the difference between chapter 7, chapter 8 is that we have to be careful with the tails in chapter 8 because sometimes we have one tail, sometimes we have two tails. But if it's a right tail test, and it only depends on our claim and then, you know, how we set up the null and the alternate hypothesis, whether we have a one-tailed or a two-tailed test. So right-tailed means we have one tail. We now put our alpha into the right tail. We don't have to split it in half because we only have one tail. And then we're going to look at what's left. So if 0.09 in the right tail, what is left over here? 0.91. So just one tail. Okay, now to find the critical value, so this is going to be just one positive value. We're going to use the area to the left, use the inverse norm of 0.91. And so we're going to see inverse norm 0.91. This is a standard normal distribution. And over here that is 1.34, which is A. So let's look at 8 and 9 as well. Okay, number 8. This is a left tail test. So what do we do with the alpha? Put it in the left tail. To find the critical value, we don't even have to label the right side because we always care about area to the left, right? We're looking for this one critical value. It's going to be a negative one. And we use what command again? Inverse norm. Always inverse norm to find the critical values. So inverse norm of 0.05 is equal to negative 1.645. This is one of the one that was rounded to 3 decimals. So, you know, label it, but also make sure you look at your distribution and see, should you have 1, should you have 2, should this value be a positive value or a negative value? So, because sometimes you may use the wrong area. Yes? So like if I had a right tail, like in the previous question, I had 0.09 in the right tail, and that's where I had to say, hey, what's my area to the left? And that's where I do 1 minus. But in this question, I'm already given the area to the left. So when I'm giving the area to the left, I'm just going to use that area. So just remember, Z distribution uses area to the left. And so you have to, sometimes you have to find it and sometimes it's given. So we'll do one more over here, number 9. Our alpha is 0.08. H1 is mu is not equal to 3.24. So even though it's not telling us whether it's one-tailed or two-tailed, we can look at our alternate hypothesis, and this is going to tell us that it is what? Not equal to means? Not equal to means it can either be here or here, right? Two tails. Two tails. So the not equal to sign means it's two-tailed. And now we have to split our alpha in half. So alpha half is equal to 0.04. 0.04 in each tail. Now to find the area in the middle, we're going to do 1 minus alpha. And that's 0.92. So 4% in each tail, which leaves you with 92% in the middle. Okay, so now it's going to be plus or minus. We have 2 critical values over here. So we know it's plus or minus. We can find either one or we can find both of them. It's easiest to just find the one on the left because that has, you know, already the area to the left labeled. So that's inverse norm of 0.04. And this is negative 1.75. And just to confirm that the right one is symmetric, to find the right one, we would do inverse norm and then add the middle plus the area to the left, and that's 0.96. So if I put in inverse norm of 0.96, it's going to be the positive one. So these are always symmetric, so that's 1.75. So plus or minus 1.75, which is A. Okay, so now we're going to do a whole hypothesis test, which is number 10. What we have to do is we have to read it very careful. We have to make sure we understand what's the parameter we're testing, right? Are we testing the mean, are we testing the standard deviation, or are we testing the proportion? So over here it says a claim is made that the proportion of children who play sports is less than 0.5. And the sample statistic includes N is equal to 1,469 subjects, with 30% saying that they play a sport. You know, sometimes it's not quite as clear where it gives you the proportion. Maybe, sometimes it says maybe I want to see if like the majority or something like that. So sometimes, you know, those are kind of the key words that we look for, and we understand, hey, percentage or proportion, you know, is pretty much simultaneously used over here. So we're doing a test for a proportion. Our calculator command is going to be the one proportion z test. And once you figure out, you know, what type of problem it is, you can go actually straight to the one proportion z test. Or you can calculate the test statistic that is given over here. So on your formula sheet, on the very bottom is the p, which is our proportion. The test statistic used is the p hat minus p divided by the square root of pq divided by n. So that takes your sample data and then standardizes it to a z-score. Then you're going to look at, is that an unusual value or not? And we're going to look at two different methods. So just to make it easy, and I really want you guys to use the one proportion z-test, we are just going to go straight to the calculator. So one proportion z-test, you're going to go to second vars. Hold on. No, you're going to go to stat test. And one proportion z-test is option 5. Then it says what is P0, what is X, what is N, and what's the alternate hypothesis. So let's set this up first. A claim is made that the proportion of children who play sports is less than 0.5. So what is our claim? P is less than 0.5. So we're now looking at the symbol over here. We're going to say, hey, does this include equality? Is there an equal sign somewhere in there? And the answer is no, right? If it doesn't include equality, then it automatically goes into the alternate. So we're going to recopy it over here. And we're actually going to say, hey, this is our claim. So we'll write claim next to it as well. What is the null hypothesis? P is equal to 0.5. The null hypothesis always has the same parameter, same number, but an equal sign over here. And we looked at all, 6 different possible ways of setting up these null and alternate hypotheses given a claim. All right, so this is important. Now let's write down what else is given. We have our sample size given. And then what's the 30%? Is it the mean? It's the proportion. So is it the population or the sample proportion? This is our sample proportion. What letter did we use for the sample proportion? What? S for the sample proportion? P and sample? P hat. Okay. And then we take the percentage and we usually convert it to a decimal number. Okay, so P hat is 0.3. Now our calculator doesn't ask us for P hat, although the formula uses P hat. The calculator uses X. X is what? You multiply, so it's P hat, it's the sample proportion times what? N. So we want to know how many of those 1,469 people actually played sport. Well, it's 30% of them, and therefore we have to multiply our proportion times our sample size in order to get that number. Okay, so over here it's asking us to fill in P0. What is P0? What should I put over here? 0.5. It is right here. It's my null hypothesis. Mike, I'm going to assume that the proportion is actually 0.5. So that is going to be the proportion from your null hypothesis, which is going to be, based on the claim. Our X, we said, is 30% off 1469, so I can calculate that right here. The only thing you have to make sure is that you get a whole number. So what happens over here? I have 440.7 people. I have to do what? Round it up to, so you're going to round to the closest number, which is 441. Okay, my sample size was 1,469. Now the next line, that tells us our alternate hypothesis. So is our alternate hypothesis, is it greater than, is it less than, or is it not equal to? So what is our symbol? It's less than. So you're going to highlight the middle one. And then we're going to go down to calculate. You can also draw it, which is kind of cool to look at the graph later on. Okay, so this restates our alternate hypothesis, which is less than 0.5. Then it gives us a Z. That's our test statistic. So it takes the sample proportion, it standardizes it to a test statistic, so that is a z-score over here, which is negative 15.32. Remember, we always rounded z-scores to 2 decimals. Just by looking at this value, do you think that's a usual or an unusual value?
Very unusual.
It is very unusual, and that's a good point because it's like when we have a value that's very unusual, we're probably going to make the right decision in our conclusion. If the value is right, on the borderline, we may or may not make the right decision, because remember, 5% of the times we make the wrong decision. So, something that is very unusual, we're probably going to make the right conclusion over here. The next one is the p-value. That is the probability. Looking at how the probability to the extreme. So what's the probability of getting at least negative 15.32, so this is looking at the area to the left of our test statistic. And it says p-value over here is 0. P-values are probabilities, numbers between 0 and 1. We always round them to 4 decimals. Over here, there's not much to round. It's so tiny. And then we're going to actually compare our p-values. So our significance level, alpha is 0.05, since there's none given. We're now going to look at how likely is this to happen by, simply by looking at how many of them are less than 15.32. And since the probability is so unlikely, we're going to go back and say what? Remember, our assumption was that the proportion is equal to 0.5. We've now calculated the test statistic, which was a very unusual value, the negative 15.32. We've also calculated the probability of getting such an extreme value. And then we say, hey, the probability is very, very low, so we go back and say our assumption was probably wrong. That's it. So when the p is low, we're going to reject the null. So this is something you're going to hear me say it all the time. When the p is low, reject the null. If the p is not low, we're going to fail to reject the null. So we go and cross out our no. We don't believe that the null stands. So that's the p-value method. The second method is the critical value method. So there are two different methods coming up with the same conclusion over here. So looking at it from a different angle, but you will always have end up with the same conclusion. So to find the critical values, we're going to say, okay, a critical value over here, I have a left tail test, because whenever I have a less than symbol in my alternate hypothesis, that's going to mean a left tail test. If I have a greater symbol, that's a right tail test. And if I have a not equal symbol in my alternate hypothesis, that's going to be a two-tailed test. So my symbol is less than, so it's a left tail test. So what I have is I'm going to find the critical value with my alpha just in the left tail. So I'm going to look at what is that value that separates my likely from my unlikely values. So since no alpha is given, we said we're going to use 0.05. So this is our area in the tails, or in the one tail in our example. We don't have to label the right side, because all we need is the area to the left to find this critical value. So we're going to use inverse norm of 0.05. And what is inverse norm of 0.05? 645. Okay, so we have negative 1.645 over here. We have now our critical region, which is to the left in the left tail test. This is called our rejection zone. So anywhere in this area, we would reject the null. Where the other one is our fail to reject zone. So if it falls somewhere over here, we would say, hey, that's just normal sample fluctuation. Sometimes it's a little less, sometimes it's a little more. So that's the fail to reject zone on the right and the rejection zone on the left. So our test statistic is going to fall way into that tail, because it's way less than negative 1.645. So it falls into rejection zone, and therefore our conclusion is reject the null. So critical value is negative 1.645, just a negative one because it's a left tail test. And so now we've done pretty much the whole hypothesis test. We found our test statistic. We've found the p-value. We found the critical value. We've drawn our curve. We've come up with our conclusion. The very last thing is to write down the final conclusion. This is where we take the original verbiage from the question and we're going to restate it. So on the last page of your formula sheet, you have a wording of the final conclusion. In the wording of the final conclusion, it asks a couple of questions. Oh, I can't zoom out. Okay, so the first question says, does the original claim contain the condition of equality? Is there an equal sign in our original claim? No. So we're on the bottom. Then it says, did we reject the claim, or did we reject the null, yes or no?
Yes.
Okay, we rejected the null, so therefore our conclusion is going to be the sample data support the claim that, and then you just restate the claim. Okay, so the sample data support the claim. So you're simply copying the first part down, and then you're going to have to go back and look at what was my claim, or what was that claim. The claim is that the proportion, right, of children who play is less than 0.5. So the sample data support the claim that the proportion of children who play sports is less than 0.5. Okay? And that's obviously a big topic nowadays with child obesity rates and everything. So you really want to look at the wording of your final conclusion. You're going to look at, ask yourself these questions. Notice that looking through the final conclusion wording, the strongest conclusion we have is the one we just got, the sample data support the claim. This is how you want to phrase your question. So whenever you come up with your own research question, you're going to phrase it in such a way that your claim goes into the alternate hypothesis. And you do that by simply saying, hey, my claim is that P is less than a number, or your claim is that P is greater than a number, because when you don't have equality in your claim, it automatically puts it into the alternate hypothesis. So that makes sure that you're down here. And then hopefully you're going to reject the null so that you have that strongest wording, which is the sample data support the claim. Read all the other ones, they're just not as strongly worded. There's sufficient evidence to warrant rejection of the claim. Okay, so we believe that the claim is wrong, right? There's not sufficient evidence to warrant rejection. So now we're really saying, well, we don't really know, we just have to do more research. And then the last one is there's not sufficient sample evidence to support the claim. Again, it's not as strong, and this is the reason why you want to make sure that when you formulate your own research question, put your claim into the alternate by either putting a less than symbol or a greater than symbol.